So looking at number 2 from exam 4 from 2014. Let's take a look at these. They're asking for each set of resonance structures, circle the form that is the most stable and explain why. So is there any one particular? D. Let's look at D. So let's look at D. So we have alright, so we'll do what we always should do, and that's of course do what? Number our carbons. 5, 1, 2, 3, 4, 5. What else do we always do?
There's a plus charge in the carbon. I mean the.
Oh, missing a plus charge, right? So that's good. Make sure I drew the right thing. That'd be the first step. Plus charge of carbon 1. What else should you always draw in? Lone pairs. So where should I put lone pairs in this case? Bromine. How many lone pairs does it have? 3 pairs. So what do we see as the major difference here for which structure is more stable? So if we call this one A, and this one B, what's the difference between A and B? So where are the carbocations at? So when we usually think about carbocations, we think about, there's 3 ways to stabilize carbocations, right? We can stabilize by hyperconjugation, right? Which is sigma bonds 2 bonds away. We can do pi bond resonance. And then the best way is lone pair resonance. So for this one, right, carbon 3 and carbon 1 are both, they're kind of secondary carbons. They both can be stabilized by pi bond resonance. But in one of these, the plus charge is closer to the most electron dense molecule, or atom, I guess. Which one of these has the plus charge as close as possible to the most electron rich atom? A does, right? So that makes this a more stable resonance contributor. Just because, right, the lone pairs on the bromine are close to that plus charge. Obviously, we could take it a step further, right? What would the best resonance structure be for this molecule? The best one would be moving these electrons down here, right, and having a bromine, right, with a plus charge. 1, 2, 3, 4, 5. Right, actually having the bromine with the plus charge would be the best structure. Well, now why would this, I guess we'll call this C, why would C be the best? Right, so the most stable resonance structure then is the one that of course has octets are full, right? You can't have full octets, right? So that would of course be C. But the next best one would be A, and then the next best one would be B, right? Full octets is really the best way to go.
So like what is the order?
Like this would be top, middle, bottom. Right? So remember we talked about charge separation. When we say charge separation, we mean like charges, right? Opposites attract. So if this bromine's electron rich, we want it close to the plus charge, right? We don't want it away. We want it close to it. So sticking with exam from 2014, exam 4. We're going to do 4A first. So we'll take a look at this. So the question is, determine if the following compounds are aromatic, anti-aromatic, or non-aromatic. So first you need to know how do you know if something's aromatic? What are the 2 requirements for aromaticity? Uninterrupted pi system, that's planar. And what's the other thing? Odd number of pair of p orbital electrons. So an uninterrupted pi system, odd number of pairs of p orbital electrons. So we have 1, 2, 3 pairs. What about boron? So we always, if you're not sure, look at the periodic table. How many valence electrons does boron have? How many valence electrons does boron have? How many valence electrons does boron have? 3. Yep. It has 6 electrons around it, but it only has 3 valence electrons. So does boron have a full octet? No, because 6 is not 8. Right, just kidding. Finals weak brain, right? Boron does not have a full octet, right? So it only has 3 bonds and 6 electrons around it. So it's very similar to what as far as its hybridization state. What's the hybridization state of this boron? sp2. It's sp2 hybridized. Meaning it has what molecular orbitals?
3 sp2 and a p orbital.
How many? What was it?
3 sp2
3 sp2s
and a p orbital.
and 1 p orbital, that's right. So the 3 sp2s are for these 3 bonds, and then we must have an empty p orbital, right? So this boron has an empty p orbital. So the question then, does it have an uninterrupted pi system? It does. Does it have an odd number of pairs of electrons in the p orbitals?
Yes.
It does. So this compound is aromatic. Very good. Take a look at E as well. So for this one, again, we need to understand what the requirements are for aromaticity. And also need to recognize, right, that elements will choose to be sp2 hybridized, to have a p orbital, to be a part of a pi system, right, to help spread those electrons around. So this nitrogen, right, what we should do is do what for all of these? Draw in our lone pairs, right? That'll be very helpful. Draw in the lone pairs, right? Because nitrogen wants to have how many bonds? 3. So if it has 3, then it has a lone pair, right? Because it has how many valence electrons? Right? Basic stuff, right? Back to the basics. So now we look at this and say, okay, this nitrogen right here, what's the hybridization state of that nitrogen? sp2, how'd you know that? Even more simply, how do you know that nitrogen was sp2 hybridized? It has a pi bond, right? It has 1 pi bond. What orbitals form pi bonds? P orbitals. So I knew that was sp2 hybridized. But it also should tell me something about this lone pair. What hybrid orbital is that lone pair in? Can it be in a p orbital?
No.
No, because the p orbital is being used for this pi bond. So that means this lone pair must be in what hybrid orbital? sp2. Right? Notice how I box in the hybridization state, and I do not box in the hybrid orbitals. Right? So what about this nitrogen? So this nitrogen has a choice. Right? It has a choice. Normally this nitrogen would be sp3 hybridized, right? To get everything away from each other. But in this case, it's right next to pi bonds, or p orbitals. So this nitrogen is going to make a choice to be able to spread that lone pair out. And what hybrid state is that nitrogen going to be in? sp2. Now it's going to do that because when it does that, this lone pair goes in what orbital? A p orbital, which then makes it part of what system? The pi system. And now we have an uninterrupted pi system, right, of p orbitals, and we have 1, 2, and now this lone pair, because it's in a p orbital, is part of that pi system, so we have 1, 2, 3, an odd number of pairs of electrons in the p orbitals, so this compound is going to be aromatic. Right? So let's take a look at for C. All right, take a look at 4C then. For this one, drawing our lone pairs. So who should have a lone pair here? Oxygen. All right, this is your classic oxygen has a plus charge. But does the oxygen really electron deficient? What's electron deficient? That carbon right there is actually electron deficient, right? So Lewis dot structure lying to us. It's fine. So how do we figure out the hybrid state of this oxygen is what? sp2. And you knew that because it's got one pi bond, so it has to be these 1p orbitals, so it's sp2. And in that case, what is this lone pair part of? What hybrid orbital is that lone pair in? Has to be in an sp2. So are those lone pairs? Is this lone pairs part of the pi system? No, it's actually perpendicular. It's 90 degrees away, so it's not part of the pi system. Is this compound aromatic? Well, it's an uninterrupted pi. Everything's uninterrupted. It's flat and it's in a ring. And there's 1, 2, 3. Right? So that's odd. So this is also aromatic. So one of the things that's kind of confusing is when we call a compound aromatic, that doesn't mean the whole compound itself is aromatic. Right? I will call a compound aromatic if one part of it is aromatic. So an example of that is this. So I would call this compound aromatic. Not because this part's aromatic, because this part's aromatic. So I would consider the whole compound aromatic, even though there's one spot that is aromatic, right? So we would say this compound is aromatic. Does that make sense? Right, even though this part is not aromatic. So only one part of the molecule is aromatic, but we call, just as we talk about things, we call everything aromatic if it has one part that's aromatic. That's a little confusing. Okay, now taking this a step further, let's talk about a compound. Let's talk about furan. Furan. So this compound is an aromatic compound. All right? This oxygen is sp2 hybridized, has two lone pairs. One lone pair is in a p orbital, and one lone pair is in what orbital? sp2. Very good. Only one of these lone pairs can be delocalized. Which one can be delocalized? Just the p, right? So delocalizing essentially means that you can just share electrons, move electrons around the pi system, right? It doesn't have to be a lone pair, right? It could be, right? I could say I'm going to delocalize these two electrons and move them to that carbon, which would be showing you something like this then. Put a negative charge there, a plus charge there, right? I didn't necessarily use the lone pairs, right? But I've moved these two pi electrons, right? It's very unlikely I would do this, right? Because but the big point is, only one of these lone pairs is part of the pi system. For anything part of the pi system can be delocalized. If you're in a pi system, that is delocalizing the electrons, right? So any electrons in the p orbitals in the pi system are delocalized. Good. Now, one of the things we talked a little bit about, so besides these kind of things, is, right, so aromatic's good, non-aromatic, neutral, anti-aromatic, bad. So one of the examples we talked about was octatetraene. Octatetraene. And when we talked about this, we said, well, right, what are the requirements to be aromatic? You need to have an uninterrupted pi system and be planar, and you need to have an odd number of electrons in your pi system. So if you just looked at this, you'd say, well, shoot, right? These are all sp2 hybridized. It looks like an uninterrupted pi system, and there's 1, 2, 3, 4 electrons in the pi system, pairs. That's even. So we would say, well, this must be anti-aromatic, right? We would guess this is anti-aromatic. But then you should think and say to yourself, wait a second. Things, if they can avoid being anti-aromatic, don't you think they would try to? Yes. So what this molecule does, it actually doesn't allow itself to be planar. It puckers like a cup. Let's see if I can draw it well. Probably not. Oh, there you go. So what it essentially does, it says, forget this, man. I'm going to become like a little cup shape, and I'm going to avoid being planar and having an uninterrupted pi system. Because having an uninterrupted pi system makes me anti-aromatic, and I don't want to be anti-aromatic. So I'm going to be puckered, right? And get myself into a conformation such that my p orbitals no longer all line up. And now this becomes non-aromatic, right? So it's trying to avoid being anti-aromatic, right? I did give another example. You could make that maybe you could look at on 4, all right? All right. 4, let's see, from exam 4, 4b. So I wrote this one as anti-aromatic, but in reality, right, I gave points to people that said this as well. Right, you could say, oh, okay, there's this nitrogen, it's in this ring, and it has a lone pair, but this nitrogen has a choice, right? The elements always have a choice, right? Is it going to choose to use its electrons for good or evil? Is it going to choose to use its electrons for anti-aromaticity? If it doesn't have to, will it? No. So, and I don't know the answer to this. I'm just making, at some level, we're talking about theory, right? This nitrogen, if it's sp2 hybridized, right? If this nitrogen says, I'm going to be sp2 hybridized, this lone pair goes where? Into what orbital? A p orbital. In which case, now it's 1, 2, 3, 4. That'd be an anti-aromatic system. So, or this nitrogen can make the bold choice to be what hybridization state? sp3 and say, forget it, man.
Okay.
It could make that choice, and that means these electrons are in an sp3 orbital. Now, I don't know if it does or not. Both answers would be fine, but that's the kind of thing we're thinking about, right? We're trying to think, well, what is the result? If this is sp2 hybridized, well, then this is in a p orbital, and then that's anti-aromatic. It could also be sp3 hybridized, and then this would not be in a p orbital and now this no longer would be an uninterrupted pi system, right? So it's kind of the idea of saying, this nitrogen saying, I'm going to not be that hybridization state, kind of like this is puckering to not be anti-aromatic. So this could be either, this is somewhere probably between non-aromatic and anti-aromatic.
So if you put like non-aromatic, you have to label that one pair sp2.
Yeah, so that's right. So so if you said this was anti-aromatic, then this lone pair better be in what hybrid orbital? A p orbital. If you call this anti-aromatic, then this hybrid orbital is in a p orbital. If you call it non-aromatic, this hybrid orbital is in a sp3 orbital, right? So it really depends on how you answer it too. Number 8 from 2014. Exam 4. So for this one, we're on detailed mechanism, and we're working with an alkyne, an internal alkyne. And what we have in our little reaction mixture is Hg2 plus, H plus, and water. And this is going to make a ketone and remake H plus. So obviously H plus must be a catalyst in this case, right? And Hg2 plus is a catalyst as well. You can write that on there. Whoop-de-doo. So one of the first things you need to think about is what's the first thing that gets attacked. So normally I told you guys, right, one of the best electrophiles, if not the best electrophile, is H plus. Unless there's something with 2 plus around, right? So what's more plus? 1 or 2? 2 plus or 1 plus? 2 plus, sure. So the first thing that's going to react is actually the Hg2 plus. But before we do any of that, of course, we're going to do what? Number our carbons, because it was written in the beginning to number thy carbons. Balance thy charges and number thy carbons. I just did 5. I didn't forget those guys out there. It's fine. Pi bond attacks. Electrons come back from the mercury as well. Usually there'll be a lone pair drawn in there, right? We form what, this mercurium complex? That's a syn addition, remember? So what do? We added mercury. So it's Hg2 plus. Yay. Number of carbons, 1, 2, 3, 4, 5. Let's try to number those same carbons on our products, right? Hopefully you can see 1, 2, 3, 4, 5. So it looks like, right, what do we need to do? We need to add what? At the end of the day, what are we actually doing?
Adding the water, OH to carbon 3.
Carbon 3, right? We need to get an oxygen on carbon 3. Everybody's with me on that? So the other thing that happens here is we have water in the system, and water is a solvent, so we have a lot of water around, right? So we just made a really good, if this was the pi bond was a nucleophile, this is an electrophile. This mercurium complex is a nucleophile or electrophile. Is it electron rich or electron deficient? Deficient, and specifically where are we going to attack, do you think?
1 and 3.
Carbon 3, right? We could attack 2, right? 2 and 3 are equally substituted, but looking at the final product, which carbon do I need to put something on? 3. So that's probably where it needs to go. So what's my best nucleophile in the system? This is water, right? Certainly not H plus, right? Is H plus a nucleophile? No. So let's have water attack in a trans fashion and make that anti-addition. So now we have our alkene. Hg now has a plus because it got electrons there. Water also has a plus charge, right? We need to balance our charge out. Right? We had 2 plus to start. We need to have 2 plus here in the end. So what do we need to do next? Tautomerization. So we can do a tautomerization, which essentially means, right, numbering our carbons again. 1, 2, 3, 4, 5. It's almost like an internal nucleophile electrophile reaction. So within here, what's a good electrophile? H. My good nucleophile is the pi bond. So let's have that pi bond go there. These 2 electrons can go there. All right, make a new pi bond. So now what do we have? Now we have this oxygen with a plus charge. Isopropyl, a new H. We still got that stinking mercury though, right? And we don't want mercury, right? Remember alkyl mercuries will kill you? Bad. So what we need to do is get rid of that mercury, right? So let's get rid of the mercury, right? Let's have the mercury take these 2 electrons and say bye, and give those 2 electrons back to the oxygen then. Right, so now mercury just lost more electrons. So it was plus 1, now it's going to be plus 2. And that's where we need it to get to, right? To regenerate it. Drink it down some more. So let's see what we have. We just remade what? The enol. Oops. The pi bond there, sorry. OH. Alright, number of carbons. Looks like I lost a carbon, that's bad. Don't do that. Alright, that's how we number them. I did number them here though, because that's why I'm confused. 1, 2, 3, 4, 5. So there's a new pi bond between which two carbons? 2 and 3. So let's just start there. OH. 1, 2, 3, 4, 5. So this is back to an enol, right? So this is really a tautomerization as well. We just went from a ketone to an enol form, right? But now we're going to go back from an enol back to a ketone, because at the end of the day, right, we need to make a ketone. And have we used that H plus yet? Let's use that H plus. What do you say? So now we're ready to use H plus. So let's use the H plus. Let's say these two electrons go there, and then this pi bond attacks. So what happened here, this H became what? It became H plus. And now this, that H, right, if I put a little label, if I put a little red star on that H, where did that end up at? And if I put a little blue star here, let's make sure we know where they're going. The 1H, that's where my red H is at. And then the new H plus is the blue H. And that gets us to our ketone. Number our carbons, 1, 2, 3, 4, 5. Alright, so the tricks here, use H2 plus first. You get it on there, make sure you have the oxygen attack the carbon that it's supposed to. Right, we need the ketone to be. Tautomerization. You get to a ketone, but you still have the mercury on there. Got to get rid of that mercury, right? So at this point, you still had, right? So this was like losing Hg2 plus at this point with a lone pair, right? That's what went away here was this. Get back to another enol. The H plus in there helps you turn this enol back into a ketone, and the H plus is a catalyst. So one of the things we talked, I showed you guys was I showed you one of two forms, particularly when we were trying to do make a trans alkene, add H's trans. This versus, so you have a Li plus here versus this form. So technically both of these are exactly the same, right? Lithium bond to carbon is always going to be an ionic bond. So you could show it like this with just a negative charge and the lone pair is there, right? Because these two electrons are the same as these two electrons, right? There's no difference. So either way, how you want to draw it. I think last year I drew it more like this. For some reason this year I drew it like this. Two electrons in a bond, but the biggest thing is, anytime it's just like seeing, right? If you saw NaCl, what kind of bond is that? It's an ionic bond, right? So you should just recognize that, even though, right? Even though that looks just like, right? This is the problem. This looks the same as this, but they're not, right? Because this is an ionic bond, this is a covalent bond. So if you see lithium bond to carbon, you should recognize that has to be an ionic bond. It cannot be a covalent bond. So you could draw it like this, but no, it reacts like this. Yep, excellent question. Number 3 on exam 4 from 2014. This one's asking us to draw out resonance structures and then evaluate which resonance structure is the most stable. So we start out with this. So this would be a tertiary carbocation, right? Tertiary and allylic, right? So I'll draw tertiary allylic, right? Allylic. but I asked to draw three more resonance structures, right? Draw out 3 more. So I'm just gonna go ahead and number everything that's essentially part of the pi system. Right? So I'm assuming, right, everybody knows what a carbocation's hybridization state is, right? What's that? sp2 hybridized, good. What that means it has an empty p orbital. So I'm just numbering out things that are part of the pi system, presumably. So I'm going to move one set of electrons. I'm going to move that. So nothing changed over here. There's a new pi bond where?
5 and 6. Yeah.
Between 5 and 6, good. Right, when I'm drawing resonance structures, I can draw all the sigma bonds out, right? Because one of the rules of resonance structures is not breaking what? Sigma bonds. So, right? So I can always just draw those out first. So there's that. Now what am I missing? Plus charge, and that needs to go where? 4. Very good. You can keep moving some more electrons. Break that pi bond between 2 and 3. So now there should be a plus charge where? Carbon 2, very good. 5, 6. And there's a pi bond now between 3 and 4. So now I forgot to do what? Draw in what? Lone pairs. Right, of course the oxygen has 2 lone pairs. So it can move its electrons down here. So now there's a pi bond where? Oxygen and carbon. One, 2, 3, 4, 5, 6. And where should there be a plus charge? On the oxygen, right? So now let's label these all A, B, C, and D. Which one of these is going to be the most stable? D. Why? Full octets, good. Which one is maybe the least stable? Maybe B because it's a secondary allylic, right? B is secondary allylic. I mean, you could also say it's also doubly allylic though, right? You have pi bonds on both sides, but okay. So maybe this is the least stable, and then between A and C, which one do you think is more stable, A or C? C, just because it's probably going to be tertiary again, but it's also closer to the electron density of the oxygen. So if we rank these, we had D being the best, and then we had C, and then we had A, and then we had B. Right? So we're thinking full octets, tertiary substitute allylic, and also really close to that lone pair. Secondary versus tertiary allylic, right? Tertiary is better than secondary. So D, C, A, B for rankings. So if this was going to react with something, a nucleophile, right? We could presume these are all electrophiles, right? They all have plus charges. Where would a nucleophile most likely react? At which place? Which numbered element would a nucleophile most likely react? Knowing what we know about the stability of these carbocations, where is a nucleophile going to react? At which number? At which number? What's the most stable intermediate? This is like an intermediate. It's going to react at carbon 2. This is where nucleophiles most likely react. Right? Well, think about it. If we're saying B is not very stable, is B going to exist very much? No. D is going to exist more. And so is C. Right? So those are the ones that are going to exist. That's going to be the intermediate, right? These are intermediates probably, carbocations. So these are the ones that are more stable. They're the ones that are most likely to exist. Therefore, they're probably the only ones that are going to react. So a nucleophile is going to add at carbon 2. Does that make sense?
Didn't you do that with other problem with the amine,
Mm-hmm.
didn't you say that it was a stronger base, the one that was less
Yep, so
stable?
let's take a look at that in a second. Right, so we're talking about starting materials now with that case. So when we're talking about carbocations, that's really an intermediate. That's already gone over a big hill, right? You can't just buy this in a bottle, right? This is already an intermediate of a reaction.
So anytime,
Right, so this would be something like this, where you'd have, right, here's a starting material, right? And you can either have B, which is up here, or you could have D. So you're probably never gonna make B even, you're just gonna make D. So D's the one, is this one's gonna react and form products, right? You wanna make the most stable intermediate. Now this was a little different. When I was comparing these two things, these are like starting materials. So now we want these to be reactive, right? Intermediates, we want to be stable, right? Intermediates, we want to be stable. They're the ones most likely to react. But for starting materials, we want them reactive. So in that case, right, these lone pairs in each of these is how we're looking at how basic they are, how reactive they are. Remember, these lone pairs can do resonance, meaning they're not as available, meaning they're not as reactive, meaning this is going to be more reactive and basic. So looking at the bonus for exam 4 from 2014. Whoops. We'll flip it upside down. Here you go. We have this phenol, and the question is, it's going to react with E+, and the question is, what's in the box? And one of the byproducts is H+. Right, so this is a little tough. So what do you have to guess from this, if you look at the products and the reactants? So what?
There's gonna be ketone.
No, well, there's going to be, but what, I mean, overall, what's happening?
There's gonna be H plus
The H plus is a product, which means what? Where did that H plus come from? Where did it have to come from? Had to come from the starting material. And where did the E plus go? On the starting material. So which, is it this H, or is it one of these 5 H's? It has to be one of these 5 H's that gets replaced by an E plus. Right? Think about it. Right?
I thought the ring was stable, so.
The ring is stable, but E plus is a really good electrophile. And I'm telling you we're making H plus. And it just so happens that this oxygen, can you draw some resonance structures with this oxygen since it's right next to that ring? Could you draw some resonance structures? What would you do? Would you push electrons into the ring or out of the ring with those lone pairs? Into the ring, right? So if I push electrons into the ring, that means these electrons need to go where? To that position, right? So what does that look like? Maybe negative charges there. So what does that tell you about if I number these everything 1, 2, 3, 4, 5, 6, 7. What does that tell you, right? One of the reasons why we do resonance structures, it tells us what? What's the point of all this? If we do a resonance structure of a star material, what's the point of all this?
Where it reacts.
It helps us understand where and how it reacts. So what did this resonance structure just tell us about this star material? What did it tell us? Is it, well, E plus is going to be what? An electrophile or a nucleophile? Has to be electrophile. That means, what does this have to be? If it's going to react, this has to be the nucleophile, right? Where is it nucleophilic at? Carbon 3. That's one place it's nucleophilic at, right? Carbon 3. Everybody see that? You could also say it's nucleophilic here too, but right, we do resonance structures, right? Told us, oh, it's electron rich at carbon 3. Let's draw another resonance structure. Now where's the electron density at? Which carbon? Carbon 5. So what's that tell you about carbon 5? It's a nucleophile, right? It's nucleophilic, right? It's electron rich there. So either one of these, right? And I could do this again, but you'll notice 3 and 7, are they the same carbon? Yep, they're the same. So you'll see here, right? Either one of these can react with E plus, right? So let's do which pick? Let's do, you want to do 3 or 5? 5. So 5 is going to react with E plus. No longer a resonance arrow, right? Now I've now double-headed. Now I'm doing one side, so I'm doing the reaction. So what do I have at the end of the day? It looks like this. We got to make sure we do what? Balance our charge. What was on carbon 5 all along? There was an H there all along. The dark H. Right? E's there. Have I balanced my charge? Well, I added E plus, and this was minus and a plus, so that's neutral, and then a plus, so I'm still at plus. So did I balance my charge? Try again. I added in a plus charge. I had a negative and a plus. So here I should overall be what? Plus. So I'm good. I need to get rid of this, right? And somebody already mentioned this. This compound is aromatic, right? Do you think it wants to go back to being, is it aromatic right now? When I started doing this, it stopped being aromatic, right? Do you think it wants to go back to being aromatic? Yep. So what's it going to do? Going to kick those electrons down, go there, go back up there. 1, 2, 3, 4, 5, 6, 7. You see that? So I just lost H plus. This is the H plus I just lost. And here, what I've done, got back to that OH, right? See, as this H leaves, it forms a new pi bond between 5 and 6. 1, 2, 3, 4, 5. Oops, 6, 7. Forgot my E, which is now on carbon 5. All right, as this H leaves, it becomes H plus. New pi bond between 5 and 6. The pi bond between 6 and 7 moves between 2 and 7. The pi bond between 2 and the oxygen goes to the oxygen, gets its lone pair back, and that's our final product. This is called an electrophilic aromatic substitution. You will learn this next semester.